Hello, welcome to Michael Shelton's Tech Tip number 4 on high temperature hydrogen attack, HTHA. This Tech Tip number 4 reveals the HTHA attack mechanism as well as a method to identify areas of likely attack. High temperature hydrogen attack is extremely hard to detect. Resultant microfissures are not readily detectable by guided wave ultrasonic testing, by conventional UT, nor by acoustic emission testing. Michael Shelton is a hydrogen subject matter expert with experience in hydrogen facility design and hydrogen temperatures up to 1560 degrees F, 850 degrees C. So let's dive into high temperature hydrogen attack as we seek to understand this serious industry issue. Mr. Michael Shelton.
Thanks again, John. This is Michael Shelton. Let's look at HTHA. In HTHA, surface decarburization and hydrogen ingress into the metal lattice may form bubbles or cavities, microfissures, and fissures. These captured hydrogen ions may combine with freed carbon ions during the high temperature to form methane gas in much the same way as hydrogen ingress at lower temperatures forms hydrogen gas in the metal lattice. These metal dislocations, under the pressure of the accumulated methane, combine to form cracks which then lead to embrittlement. Therefore, early detection is critical for such operating scenarios that promote HTHA. Both API 941, steels for hydrogen service at elevated temperatures and pressures in petroleum refineries and petrochemical plants, and API 571, damage mechanisms affecting fixed equipment in the refining industry, deal with inspection for HTHA. Advanced ultrasonic backscatter techniques, AUBT, have proven the most successful. Usually the backscatter method, depth of damage, is further refined with velocity ratio and spectral analysis for backscatter result confirmation. The real issue with HTHA inspection, which again is AUBT now, is that it is very localized. No global inspection technique yet exists for HTHA inspection. HTHA is also a function of the stress state of the metal exposed to the high temperature hydrogen attack. Thus, it is very important to identify the high stress areas when determining the optimum locations for the localized AUBT inspection points. An appropriately designed inspection plan for a vessel or piping undergoing HTHA will include high stress area identification as worst case. Since HTHA is both a stress and temperature phenomena, hot areas in addition to stress areas should be considered. In all, a carefully engineered inspection plan is required. Therefore, HTA inspection requires sound engineering, usually finite element analysis assessment of the vessel, equipment to be inspected, and a comprehensive step-by-step plan. Normally, vessels which operate within 50 degrees of or above the metal's Nelson curve criteria, again API 941, will require a structured inspection plan. Let's look at methane buildup. High temperature hydrogen attack is similar to hydrogen embrittlement, except that as ions migrate into the metal lattice, the high temperature presents the hydrogen ions trapped in the lattice with a carbon ion. It is this 2CH4, again, methane gas, that acts identically as the H2 gas formed with the hydrogen ions trapped in lower temperature metal lattices, both leading to hydrogen embrittlement. One is at a lower temperature and the other is at a high temperature, HTHA. Well, since we're talking about high temperature here, let's look at the upcoming tech tip number 5, which will be on ASME B313, Appendix V, high temperature. See you there.